Go for it.
Thanks, Andy. I'm trying to find my camera to turn on, but I can't find it right now, of course. So I guess you don't get to see my face. I'll just go ahead and get started with this. A little bit about where we're going today. We're going to talk about how to prepare for your survey, and then how to do the survey at the crossing location, and how to do your survey at the reference reach. So before going into the field, here's a few things to think about. You want to get utility locates done. Look at your aerial imagery. Get LiDAR if it's available. Check out the 80 F&G culvert survey online, and you might be able to even get a crossing slope off of that, as they've done some longitudinal profiles on a lot of these culverts that have been surveyed. Look for potential reference reach locations in your aerial imagery. Get property ownership. BLM has a website for that. That's useful, or a lot of the boroughs and municipalities have property ownership websites. And my favorite, get permission from the landowner, of course. And then my favorite is checklists. Look at your checklists, create checklists, because there's always something that's going to get forgotten if you don't have a checklist. So the crossing the features that we want to pick up at the crossing are the stream crossing longitudinal profile, the road, any structures, underground utilities and overhead utilities, any major vegetation lines, topography around the road and crossing area, and the ordinary high water mark within about 100 feet of the crossing usually is sufficient for that. And here's what all of that data looks like after it's brought into CAD. Note that the longitudinal profile extends well beyond the road, whereas the ordinary high water mark is which is the blue line is the ordinary high water mark, and then the longitudinal profile is this magenta line. For the longitudinal profile at the crossing, we are looking to establish the natural stream slope outside of the influence of the road, which may be acting like a dam and trapping sediment. So you will need to capture enough stable grade controls upstream and downstream of the crossing to, let me get my laser pointer here, sorry about that, upstream and downstream of the crossing. So we need enough of those to establish the natural slope. We recommend a minimum of 4 stable grade controls for uniform profile, 2 upstream, 2 downstream. If there's a slope break, then capture 6 grade controls minimum, 3 upstream and 3 downstream. It's okay to use the tailwater crest as one of those grade controls unless you suspect that there is excess sediment downstream from a previous road failure, as is the case here. You will need to go outside of the right of way, so make sure you get your landowner permissions if it's public land or if you're not in a navigable waterway. And the moral of the story is go farther than you think you need to, because it's really hard to know in the field where this area of aggradation might stop and start. And this is just a photo of an example of aggradation upstream of a culvert. It's not always going to be this obvious. This one's pretty obvious. So don't forget to get the existing culvert dimensions, top of culvert, invert of culvert, the water surface, the structure width, and the rust line can be helpful. Rust line might tell you, you can use the rust line to back calculate what the ordinary high water might be, because that would be the typical annual wetted, or might be the typical annual wetted line. Anyway, just a piece of information that might be helpful. You'll have to determine whether that makes sense or not. And of course, the road elevation. Also, as Franklin mentioned yesterday, you can measure discharge when you're out there, and that can help you to understand low flow conditions, or it might help you to calibrate a HEC-RAS model if you're using one. Selecting reaches that meet project objectives, appropriate slope, single thread, and not a relic channel is critical. Avoid the D, DA, and the F and G stream types for your reference reach. Reference reach should be within 25% of the target crossing slope. We also may need to go higher in the watershed to find a reference reach if a steeper crossing is desired to meet your project goals. We use an upper limit of 4% for juvenile fish passage for crossings located on B, C, D, and E stream types. If your crossing is an A stream type, then you can generally find a reference reach near your crossing that meets your project goals. So what I'm saying there is A stream types are going to be steeper, and so of course your crossing is going to be steeper. A pristine reference reach is difficult to find. Pristine means no human impacts, even in Alaska. But we can use reference reaches that have been impacted as long as they are stable and have formed bankable benches. These may be very small, disconnected benches. This aerial shows the Little Tonsina River off the Richardson Highway. You can see here that a section was channelized about 50 years ago or more. And you can still see the historical meandering channel in the images. The channelization that took place here steepened the slope and caused a head cut to occur well upstream of the little red dot you see there, which is a culvert that we plan to replace with a bridge. The channel is now stable and no longer head cutting. However, due to the historical head cut, the river still has not reestablished new banks immediately upstream of the culvert, and it's an F stream type. So we went further upstream to get out of the influence of the head cut and get into, I think that's a Rosgan E stream type. I'm going by memory there. But anyway, we just wanted to get out of that impacted area. And these are photos from that same area. So this is the channelized stream downstream of that culvert. And here's what the reference reach looked like. And we want to avoid channelized streams, but also, or I should say man-made channelized streams. Any streams with this debris can affect the channel morphology. We also want to avoid areas of excess erosion because that may be indications of channel instability. And we want to avoid degraded stream types. So the selected reference reach at this crossing is outside of the influence of the culvert. I would prefer to have a reference reach that is upstream of the crossing if possible, because it helps to understand the sediment supply at my crossing. But upstream is not good at this site because the road is acting as a dam and impounding flow. So we have a wetland upstream and downstream, but the wetland upstream is at a higher elevation than it should be naturally. Also, due to this impoundment, we expect that only fine sediments will be moving through this crossing, just something to think about when you're designing that crossing. So we're going to collect our longitudinal profile, our flood prone width, our cross sections, site map, pebble count, key pieces count and sizing, and the sinuosity at this reference reach. So a word about stream geometry, which is useful for understanding what you're capturing in the longitudinal profile. The top image shows the plan view following the Thalweg of the channel. And you'll notice it does not follow the center line of the channel. So the thalweg is the lowest point. And it also shows riffles, runs, pools, and glides. In the bottom image, we can see the corresponding profile showing the stream bed, water surface, and bankful. Use that water surface to help locate your channel features or bed forms. Real surveys, of course, are not this perfect. Water surface measurements, I want to note, need to be done at steady flows to be useful. Flows can change from day to day or even between morning and afternoon. So here's a real reference reach profile. Note the X's. These were features that we thought might be bankful, but after looking at all the evidence back in the office, we determined that they were not. Survey in every surface you think might be bankful is a great idea, and then you can use the clues you get back in the office to determine which ones really are bankful. And of course, capture at least 3 stable grade controls, and the reference reach should be minimum of 20 times the bankful width and length. So the orange triangles show the grade control structures or natural grade controls, not structures. And the yellow line shows the natural slope of the channel. So we connect the grade control structures to get the channel slope. Note that that should match the bankful slope. And another way to look at this, I meant to draw on here, but this should also match your water surface slope. And you're going to draw your water surface slope through your head of riffle tail crest of pool water surface elevations. Vertical exaggeration is really helpful to see these features. So a lot of times when you do this in CAD, the vertical exaggeration isn't all that much. I really recommend increasing your vertical exaggeration by quite a bit. A pebble count. So we got 2 pebble counts minimum that we need to do. One is for the entire reach, and we're going to do 100 pebbles, divide that up into 10 cross sections at equal spacing, and get 10 pebbles at each cross section. And then our riffle pebble count is all going to be done within the representative riffle, and we're going to get 100 samples there. Again, 10 cross sections, but we want, or 10 transects, I should say. But we want those transects to be super close together and all within that riffle. And that riffle pebble count gets us our D84, which can be used to calculate bankful discharge. This is just a pebble count data sheet. Make sure you measure the B axis. And the flood prone width will help us to calculate our entrenchment ratio. The flood prone width is the width of the floodplain at 2 times the maximum bankful depth.
Hey,
so a riffle.
Going to give you your time warning there. Thank you.
All right, thanks, Jess. So the riffle cross section, it's super important that we are very accurate on this cross section. We don't want to see like 4 data points, which a lot of times I get when I send a surveyor out without assistance from us. So make sure you get that real accurate. And these are the dimensions that we're going to be mimicking in the channel at the crossing, and it's also used to calculate the bankful discharge and to classify the channel. So yeah, just accuracy is important there. And this is a fun diagram that we wanted to share because it summarizes multiple clues that you can use to identify bankful. I recommend listening to Matt's geomorphology talk if you missed that for a thorough explanation of identifying bankful features. Identifying bankful can be very challenging.
Fortunately, there are desktop methods we can use to confirm our bankful geometry back in the office. This is a bankful geometry verification. We're going to use the D84 of the riffle pebble count data to estimate roughness. There are several methods of calculating Manning's N. Be aware that some methods may not apply to your stream type. Use the Manning's N and the relative roughness equation and the bankfold channel geometry from your representative riffle to calculate the bankfold discharge. Next, compare your bankfold discharge to your gauge data and regression equations. Note the difference here between the values that the gauge data gave us for the 2-year flood flow and the regression equations. We know our bankfold discharge should be between the 1 to 2 year flood flow, and that gives us a fairly good feeling that this bankfold discharge, given the gauge data, makes sense. Comparing it to the regression equation, I might think that my bankfold cross-section is too small. However, I trust this gauge data more. We can also look at the bankfold velocity for another sanity check. That velocity should be less than 5 feet per second. Typically, it's 4 to 5 feet per second for alluvial streams. If your bankfold velocity is higher than 5 feet per second or less than 3 feet per second, you might go back to your survey data and see if there's another bankfold surface that makes more sense. And that would get you a different channel geometry. We can also use regional curve data if it's available.
So this is just an example of how you might do that. You would go in with your drainage area at 80 square miles in this example, and our bankfold area would be 200 square feet. I can do the same analysis on these width and mean depth curves as well. So we look forward to getting that regional curve data. I think that's going to be really helpful for verifying our bankfold geometry and even being able to review projects that maybe we haven't seen the site and have a feeling of whether the culvert width is reasonable based on these regional curves. We want to create a site map so we can just understand our features when we're back in the office, do our key pieces count, measure all 3 axes on our key pieces, that's the 20 largest particles in the stream, calculate the sinuosity, which is the stream length divided by the valley length. There are some other ways to use slope, but I prefer to think of it that way. And you can do this back in the office if you're using a total station or GPS. And then we're going to classify our channel using the Roskin method. So a little bit about surveying equipment. A laser level is a great tool for checking grades during construction because it can be done by one person. However, it can be really difficult to use a laser level in brushy stream survey because brush, it's just brush blocks that laser, and it's difficult to figure out what piece of leaf is actually blocking the laser. The auto level is a line of sight instrument. It's light and easy to carry. It can actually penetrate fairly dense brush, and bonus, it doesn't require batteries, which is awesome when you're remote. The total station provides X, Y, and Z position and also may have a scanning function. It provides good elevation accuracy, plus or minus an inch. The position accuracy, X and Y positions, is not as accurate as a GPS, but horizontal position is much less important than elevation accuracy. A GPS also provides, survey grade GPS also provides X, Y, and Z position. The elevation accuracy of the survey grade GPS can be compromised in Alaska because satellites are in the southern hemisphere. I suspect that some surveyors continue to survey when these satellites are no longer available, and that is what is compromising the accuracy here. But we have seen errors plus or minus 9 inches in the vertical direction on some vertical surveys. And some of these have been very critical errors that have caused construction delays and problems. So we recommend that if you're using GPS, use a laser level, auto level, or total station to spot check those GPS elevations. And we've actually written that into our construction contract requirements. Just wanted to share this survey checklist. I want to just note the division of labor between the engineer and the surveyor. Working with the surveyor helps speed up the survey and lower survey costs. So the surveyor is not out there capturing unneeded data, but you're making sure you get the data you need. And here's my survey gear checklist. Notice how many of these items have to do with bugs and bears. Be bear safe out there. Survey with at least 2 people and carry bear protection. One of the surveyors we work with was recently mauled by a bear while surveying alone. So I know a lot of folks do it, but it's really a bad idea. And I think that's all I got.
All right, thanks, Heather. Just one question